All right. Hi, guys. So today we're going to be talking about most of the important lessons from Unit 4. To start off, we're going to talk about rate laws. We're given this question here. It says, consider the reaction BF3 plus NH3 that goes to F3BNH3. We were told the reaction is first order with respect to BF3 and second order with respect to NH3. Write the rate law for the reaction and identify the units of the rate constant. Most importantly, we always want to annotate or question. These two here are our reactants. These two here are our products. And we're told that the reaction is first order with respect to BF3. I'm going to go ahead and put first on BF3 and also second order with respect to NH3. I'm going to go ahead and put second on NH3. The question asks us to write the rate law. And we know the skeletal for rate law, R is equal to rate constant K times the concentration of your reactants to some order or exponent. So write the rate law and then identify the units of the rate constant K. Okay, so this is quite simple, knowing that the skeletal for the rate order or rate law is equal to R equals to rate constant K, concentration of BF3 raised to the first power, and concentration of NH3 raised to the second power. We have a rate law, and that's it. Let me show you where scholars tend to mess up. Scholars tend to mess up when they put R is equal to concentration of BF3 raised to the first power, NH3 raised to the second power. What's wrong with this? Precisely. There is no K. It's missing a K. If you are missing a K, it means that you will get this incorrect. You have to make sure your K is present. Another way that scholars mess up is if scholars go like this. Scholars have K, concentration of BF3 raised to the first power, and NH3 raised to the second power. What's wrong with this? Exactly. Scholars have this plus sign here, and it should not be a plus sign. It should not be a plus sign. It should actually be a multiplication sign. So that makes it incorrect. Another way that scholars mess up is scholars go R is equal to rate constant K, concentration of BF3 raised to the first power, and concentration of NH3 raised to the first power. What do you think is a scholar's mistake here? I think the scholars looked at the overall equation. I was told that this does this when I double click. But I think scholars look at the first equation, the overall equation, and notice that there's a coefficient of 1 here. And so they made those into their rate order exponents. That is incorrect because the coefficients have no impact on the overall rate law. The rate orders can only be done experimentally or if they were given to you. Another way that scholars make a mistake is when scholars go rate constant K, concentration of BF3 raised to the second power, and they have concentration of NH3 raising it to the first power. That is not okay. Why? Because the order for BF3 is not 2. That's the order for NH3. The order for NH3 is not 1. That is actually 2. So you have to be paying attention to what the question says so that you do not make a mistake. Now, an acceptable answer would look like rate constant K is equal to NH3 raised to the second power and BF3 raised to the first power. So what's different about this answer here and this answer? It's just the placement of each reactant, but that doesn't matter because you're multiplying them as long as the concentrations the rate orders are the same, then we are good to go. So that's the first question. The second question that we're going to look at, or the second type of question in Unit 4, is when we talked about derivative rate law. Going to read and annotate the question. The following data were measured for the reaction of nitric oxide with hydrogen. We're given this equation over here. We have our reactants and we have our products, and we're given 3 trials. So when we're given these 3 trials, we want to, and we're trying to figure out the rate law and the rate constant, or even to calculate the rate, we have to look at each of these trials and notice where at least 2 trials are held constant. So if you look at the first and the second trial, we'll notice that trials 1 and 2, those are constant. And over here for H2, we notice the change is by 2. Because if you go from 0.1 to 0.2, you can multiply by 2. So the change is by 2. And over here, we notice that the change is by 2 as well. So you want to ask yourself, what is the rate order for H2? Well, we can solve for the rate order for H2 because we notice that NO is held constant. So only the reactant that is changing, we can figure out the rate order for that specific reactant. So we would set up our concentration versus rate table, and we would take the 2 that is for H2 and ask ourselves 2 raised to the what power is equal to 2? X is equal to 1. 2 raised to the first power is equal to 2. So it means that the order for H2 is equal to 1. We could do the same thing for NO. We need to find 2 trials which are constant and notice where the other is changing, where the other reactant is changing, and set up our concentration versus rate chart. So we notice that trials 1 and 3 are constant for H2, which means that we can find the order for NO using trials 1 and 3. And the change here is by 2, because 0.1 to 0.2, you multiply that by 2. So we look here at the rate, and we see that 1.2 going to 4.92, we can multiply that by 4. So we need to ask ourselves, 2 raised to what power is equal to 4? X is equal to 2. So the order of NO is equal to 2. So to write the rate law, we'll go rate is equal to K, concentration of NO, raised to NO, which is 2, raised to the second power, and the concentration of H2 raised to the first power. And that's a rate law. Remember, we don't care about our products when we are writing the rate law. Only the reactants formulas go into the rate law. It asks us to calculate the rate constant K. We need to know our units that's associated with rate. Rate has units of molar concentration per second, and K, which is what we're solving for, well, actually it did not ask us to solve for the rate constant. It asked us to calculate the rate constant. So we're going to look at the data table and figure out what the rate constant is. Okay, trying to scroll up. So rate constant K. So rate constant K, if we look at the smallest number, we will see, if we look at the smallest number, we'll see that the constant is 1.23 times 10 to the minus 3 molar concentration per second, because each time the rate was changing, it was changing by 1.23 times 10 to the minus 3. If we were to add 1.23 4 times, we would get 4.92 times 10 to the minus 3. So the rate constant here is equal to 1.23 times 10 to the minus 3. And the units were given to us in the data table, and it's molar concentration per second. For question number 3, it says calculate the rate when NO is equal to 0.050 molar concentration and concentration of H2 is equal to 0.150 molar concentration. So if we have the formula, rate is equal to concentration of K, concentration of NO2 raised to the second power, concentration of H2 raised to the first power. All we have to do is substitute in our values, and we know from part B that the rate constant K is 1.23 times 10 to the minus 3 molar concentration per second, and we know that the concentration of NO2 is not NO2, but NO is 0.050 molar concentration, and we're squaring that. And then the concentration of H2, which is 0.150 molar concentration raised to the first power. If we were to put that in our calculators, go ahead and put that in your calculators just to verify that we have the same answer. If you were to put that in your calculator, you would get 4.6125. 4.6125 times 10 to the minus 7 equals to, with the units of 1 over m squared s. And that's it for C. So I'm going to go over some half-life problems because that was lesson 4. So example question 2, I'm going to start with that one. How long will it take? So we're solving for time. For a 40-gram sample, I would bet this is our initial amount. With a half-life of 8 days to decay to 1.5 grams. This is our ending amount. So we always want to set up our time and an amount chart. You could do it horizontally or vertically. Time and amount. So we always want to start at time 0. And the amount that we had initially was 40 grams. The half-life they told us is 8 days. So in order to decay to 1.25 grams, I think. Yeah. In order to decay to 1.25 grams, we need to each half-life reduce the initial amount to make it half of what we started with. So half of 40 would be 20. Then half of 20 would be 10. Half of 10 would be 5. Half of 5 would be 2.5, and then half of 2.5 would be 1.25 grams. So then we just need to figure out how many half-lives we went through or how many days it will take. Remember, we always start at time 0, and then the second row or the second column should be your half-life. Each time we go through a half-life, we're adding that half-life. So it would be 0 plus 8, that gives you 8. 8 plus 8, that gives you 16. 16 plus 8 gives you 24. 24 plus 8 gives you 32. And 32 plus 8 gives you 40. So the units that we should have for time should be days. So our answer would be 40 days. And we went through 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives. 5 half-lives in order for the sample to decay to 1.25 grams. So one area where I noticed that scholars make mistake is when they're figuring out what their half-life is. Two areas. One, scholars are not starting at time equals 0. They will tend to put time equal 8, which is the half-life. You do not start with your half-life. If you do that, you're going to mess up. Scholars will have 8 and then 40, and then this will be 16, and then it will be 20. You're going to end up with the wrong answer. You're going to have 24, and then it will be 10. Then you'll have 32, and then it will be 5. So you'll see that they're not matching. You have to start at time 0 in order to get the correct answer. Another area where I noticed that scholars will mess up is when they are adding the half-lives. I think scholars tend to do 8 plus 8 is 16, 16 plus 16 is 32, and 32 plus 32 is 64. They add more than what you need. The only time that you I don't know how to say this, but you're not doing that. You're not multiplying or adding by the exact amount that you have in your times chart. You're adding the half-life each time you go through a half-life. So let's look at example question number 1. Bismuth is often used as part of an antacid medication to treat gastrointestinal issues. A medical institution requests 1 gram of bismuth 214 with a half-life of 20 minutes. How many grams of bismuth 214 must be prepared if the shipping time is 2 hours? You always want to set up your time and amounts chart. Your time is in hours because it tells us here in the problem, and your amount. We need to actually figure out how much do we need to ship in order to make sure that when the medical company gets it, they will have 1 gram available. So the half-life time, we always start at 0, and then we go into our half-life next. The half-life is 20 minutes. So the units here is not necessarily minutes. Hours is minutes. The half-life is minutes. So then each half-life, you add 20. So it will be 40, then 60, then 80, then 100, then 120, then 140, 160, etc. We want to end at 1 gram. Well, we can start at 1 gram here, and then we know that if we went through a half-life, it would be 2, and then going forward it would be 4, going forward it would be 8, going forward it had to be 16, going forward it would be 32, going forward it would be 64. Why? Because half-life is half the time that the substance takes to decay. So that means in this previous half-life, it had to be 2 grams so that 1 could be remained. In this previous half-life, it had to have been 4 grams so that half the substance, which is 2 grams, could be remained, etc., etc. So going from working backwards to forwards, we'll see that in order for the shipment company to have 1 gram, they would have had to start out with 64 grams or ship 64 grams of the substance so that by the time it gets to them in 2 hours, it will be 1 gram. All right. If 20 grams of a radioactive isotope are present at 1 p.m. and 5 grams remains at 2 p.m., what is the half-life of the isotope? We still want to set up our times and amounts chart. We always want to start out at time 0. And then the half-life, we don't know what it is. So we're going to have to leave that blank. But what we do know is that we're starting out with 20 grams. This is your initial amount. And initially at 1 p.m., you had 20 grams. And then 5 grams remain. So we're trying to end at 5 grams. So we're going to see how many half-lives we went through. So if you had 20 grams initially, half of that would be 10. And then half of 10 would be 5. So we literally just went through 2 half-lives. So how many would remain at 2 p.m.? Well, if we know that 5 grams is remained at 2 p.m. and we started at 1 p.m., that means this half-life, it had to have been 130, which means your half-life is 30 minutes. And then we're going to look at unit 4, lesson 5. We're given this reaction mechanism, and it's proposed that the reaction occurs in 2 steps. Using the axes provided below, draw the curve that shows the energy change that occur during the progress of the reaction. The curve should illustrate both the proposed 2-step mechanism and the enthalpy change of the reaction. So we want to read and annotate everything that's going on here. This is our overall equation. And this delta H is negative, so we know that this reaction is exothermic and releases heat and feels hot. We know that step 1 is the rate determinant step, and that governs the rate law. And then we have our step 2 here, which is our fast step. So it says to draw the energy profile or the energy changes. We start out with our reactants, and it's 2 steps, so I just literally did the first step, and then I'm about to do the second step. And it's exothermic, so I'm gonna stop it there. This is my products, this is my reactants. The potential energy of my product is lower than the potential energy of my reactants. This is a 2-step mechanism. The first step is the slow step, so I'm just going to label that as my RDS, my rate determinant step. And the second step is my fast step. Notice that it's my fast step, so the activation energy is lower than the activation energy in my rate determinant step. And then it says make sure that we are accounting for the enthalpy change. The enthalpy change is the difference between our reactants and our products here. If you were to do products minus reactants, you get a negative delta H value, which according to them, it's negative 72.6 kilojoules per mole, which means that this reaction is exothermic. If this graph was endothermic, you would expect to see something that looks like this, where the potential energy of the products is greater than the potential energy of my reactants. Now, the second question says, identify an intermediate in the reaction mechanism above. To figure out what we need to know what our intermediates are. The definition of an intermediate is that it is produced in one step, then used in another step. Produced, then used. All right, so we're looking for, but the key to doing this is that we need to keep in mind that we're not disrupting anything, any one of our reactants or products that belongs to the overall equation. So C2H4, HCl, we can leave those alone because they're present in our overall equation. C2H5 is present in, or C2H5Cl is present in our overall equation as well. So we do not want to disrupt that, which means that the only 2 possibilities for our intermediates are these 2 here. But an intermediate, these could have been intermediates or catalysts. The question asks for an intermediate. We need to keep in mind the definition. Intermediate means you're produced in one step, then used in the next step. Since these 2 species are on the product side, we could say that they're being produced, while here in step 2, they are being used because you use them to make the product. So our intermediate, we have 2 options. It will be C2H5 plus and Cl minus. It says identify whether the rate determinant step is unimolecular, bimolecular, or termolecular. Now, the rate determinant step, which is our fast step, is our slow step that governs the rate law. I'm sorry. So the rate determinant step, since we have 2 reactants, one here and one here, we could say that the rate determinant step is bimolecular because we have 2 molecules that are colliding. and then it asks us to write the rate law. To write the rate law, we always have to remember that it's the reactants from the rate determining step that goes into our rate law. So our reactants are C2H4, C2H4, and HCl. We need to figure out what the order of each reactant is. Now, unlike the example that I did before, the order of the reactants come from the coefficients in the rate determining step. So it would be C2H4 raised to the first power and HCl raised to the first power. And that's it for the rate law. I'm going to skip over Unit 4, Lesson 6, and I'm going to do that in a different tutorial. I just wanted to go over Unit 4, Lesson 8. There are a few things that we need to remember about collision theory. In the first diagram above, the second reaction results in the successful formation of products, while first reaction does not. Using a diagram, explain why the second reaction successfully formed products. Now, in order for a chemical reaction to occur, we need sufficient energy and proper orientation. If molecules do not have sufficient energy, they will not collide, because we need to overcome the activation barrier for our reactant molecules. So if it doesn't have sufficient energy, the chemical reaction would not take place. And if the molecules are not orienting themselves in a way that will be favorable to produce products, this reaction will also not take place. So the factors that affect reaction rates are: 1, if you add a catalyst, because a catalyst lowers the activation energy or provide an alternate pathway. So if you see a regular reaction that looks like this, a catalyst will start out at the same exact location, but it travels a different pathway and end in the same exact location. So the catalyst lowers the activation barrier in order for the chemical reaction to take place. Additionally, if you have your temperature affects your reaction rate, because if you have high temperatures, that means there's enough energy or sufficient energy for the molecules to collide. Energy for molecules to collide, since they are overcoming the activation barrier. And because if you increase the temperature, it means that the average kinetic energy of particles will be increasing, which will increase the frequency of effective collisions. So increased frequency of effective collisions, that allows the chemical reaction to take place. Another way to speed up a chemical reaction is if you increase the surface area. If you increase the surface area, that means there's more area exposed for more effective collisions under the right conditions for the reaction to go forward. So if you have a whole pill versus pills that's like crushed, the pill that is crushed has more surface area, which means that it will allow for more collisions that will speed up a chemical reaction. If you increase the concentration of a chemical reaction, of your reactant species, increase the concentration, that will also allow for the reaction to go faster, because it allows for more effective collisions. If you have a 1 molar versus 2 molar, that will speed up a chemical reaction. If you have like 10 grams versus 20 grams of sugar, for example, that will speed up the chemical reaction. The more concentration of your species, reactant species that you have, the faster the chemical reaction will go further. All right, and I did not talk about volume, but if you decrease the volume, it allows for more collisions because there's less space, which will make the reaction go further.